I'd like to thank all the participants for participating this workshop. So and staying until the last day. And okay, so this is a joint work with the next speaker, Hwajang Lee, and who will talk about arc index of more complicated knots than these pretzel knots. Okay. Okay, so here's a slightly different definition of an arc presentation. So on the first day, No explained about some arc presentation, but this is equivalent, but a slightly different version. So in a diagram D of a knot or link L, suppose there is a simple closed curve C, this red circle, meeting D in k distinct points, which divide D into k arcs, alpha 1 through alpha k, with the following properties. And each arc, alpha I, has no self-crossing. And if alpha I crosses over another arc, alpha j, then the index I is bigger than j. And also, if alpha I crosses alpha j at another point, then it's also an overcrossing. So alpha I stays over. If it is over at one point, then it's over at every other point. Okay. And for each I, there exists an embedded disk di, whose boundary is this closed curve C, and the ith arc alpha I is on this disk. And these disks have they intersect only at their common boundary, which is equal to C. Okay, and this pair, the diagram and this simple closed curve C is called an arc presentation of this link L with k arcs, and then this C is called an axis of this arc presentation. And this picture shows the conversion of this definition to the usual definition of arc presentation. So by removing a point P from this axis, which is away from L, so if I remove a point on the red curve here, and then we identify this axis minus this point P with the z-axis, and then each disk di with a vertical half plane along the z-axis, and then this shows an arc presentation given in the open book presentation. So if I cut here and then if I open it this way, then these two arcs become these two arcs, and these three arcs outside becomes these arcs. And every knot or link has an arc presentation. I'll explain that in the next slide. And for a given knot or link L, the minimal number of arcs in all arc presentation of L is called the arc index of L, denoted by alpha of L. So a grid diagram of a link diagram, a grid diagram is a link diagram of vertical strands and horizontal strands like this, with the property that at every crossing the vertical strand crosses over the horizontal strand. Okay? So here at these three crossings, the overcrossings are vertical, and then undercrossings are horizontal. And every link diagram is regular isotopic to a grid diagram. So if you have a link diagram, then you can turn every crossing. You can turn a neighborhood of a crossing so that overcrossings become vertical. So you can do that by regular isotopy, and you can straighten all the edges by adding some corners if you need, and you can convert any diagram into this grid diagram with the same number of crossings. Yes. And once you get a grid diagram from a link diagram, then you can have an arc presentation by this open book presentation. You place an axis behind this diagram, and then pull all the horizontal arcs back to this axis so that it touches like that. Then this is an open book presentation. So every knot or link has an arc presentation. And here's another form of arc presentation. So an open book presentation of a link can be isotoped to have a bouquet projection onto a plane perpendicular to the axis. So if you look at this open book presentation from the top of z-axis, then it'll look like this diagram, and people call this a wheel diagram. And if you tilt each of these spokes, then you will have this bouquet diagram. And if you assign relative heights, relative z heights of the ends of these two ends of this loop, loops, then this has all the information of the embedding. Okay, so it'll give you the knot type or link type. These numbers. So here, so this is 1, 2, 3, 4, 5, and this loop is 1, 4. There's a 1, 4, and it is connected to 4, 2, 4, 2, and 4, 2. So 4, 2 is connected to 2, 5, 2, 5, and then 5, 3, and then 3, 1, 3, 1. Okay. So arc presentation can be given in many different ways. So this theorem by Bae and Park says a reduced non-split link diagram D with C crossings can be isotoped to have a bouquet projection with C plus 2 loops. So and here I I omitted the height information of these loops. But so here so C plus 2 is same as the number of regions in the diagram you started with. So if you have a C crossing non-split diagram, then there are C plus 2 regions, right? And what you obtain is a bouquet with the same number of leaves is same as the number of regions in this diagram.
In your definition, so your example, that example, every line is straight.
Here?
Is this?
No, it doesn't have to be straight. It can go like that.
Okay.
Yeah, right. So, but this one, everything is straight. And so in this presentation, there are two parks, and none of them is same as the park sitting down there. So this park is Chanyang Park of Gyeongbuk National University. They are both at Gyeongbuk National University. Okay, so I'll sketch the proof of Theorem 1. Suppose we have a prime link diagram D with C crossings, and then just pick one crossing, and then you so just ignore these two branches. Then it's a crossing. Then you pick one of the next crossings. Then you pull this toward this crossing. Okay, and if this arc is an overcrossing, then you place it over here. And if this arc is an undercrossing arc, then you place it underneath the crossing. Then you can keep doing that in such a way that you end up with a diagram like this. And so here, except this large one, the leaves are the number of these leaves is same as the number of the crossings. Okay, so if you look at this change, the number of regions does not change. Okay, so it only reduces the number of crossings. So the crossings are accumulated to one single crossing. So once you reach this type of diagram, then the number of regions is same as the number of regions that of the diagram you started with. So this gives you two regions, and all these loops, these simple loops have give one region. So the number of these small loops is same as the number of crossings. And after this, you pull this part over here. So this part becomes one loop, and this part becomes another loop. So you end up with C plus 2 loops. Okay. So this is the idea of band park. So what they do with the spokes, they actually embed this on vertical half planes, but this is essentially the same as their argument. Okay. So now so this construction, this construction of C plus 2 loops by band park gives an upper bound of arc index of a knot. So if a knot has knot or link has minimal crossing number C, then the arc index is not bigger than C plus 2. Okay, and we need the Kauffman polynomial for lower bound of arc index. Okay, the Kauffman polynomial of two variables A and Z is an invariant of oriented knot or link defined in this way. So A to the power minus WD times lambda DAD, and here D is a diagram of this link L, And WD is the right of the diagram. Yeah, so you can get it because it's an oriented, not a link. And lambda DAD AZ satisfies these three conditions. So lambda of this unknot diagram is equal to 1. And if D plus D minus D0 D infinity are related by they are differ by these diagrams at one local place, then they satisfy this equation. And if T plus T minus they differ by these local diagrams only, then they satisfy these relations. So I think everybody knows well about this Kauffman polynomial. And so this polynomial has integer coefficient, but it may have negative powers. Okay. So the degree in for the terms in this polynomial, the degree in A can be positive and negative. So and the A spread of this Kauffman polynomial is the maximal degree in A minus the minimal degree in A. So this is always a positive number, unless you have an unknot. Okay, and this factor 8 to the minus WD shifts the maximal degree and minimal degree by the same amount in the same directions. So the spread of this Kauffman polynomial is same as the spread of this A spread of this lambda polynomial. Okay, so around the end of this talk, I'll show you the results of computation to prove some results that we have. So if L is an alternating link, then the A spread of this Kauffman polynomial is bigger than or equal to the minimum crossing number of L. This is proven by Moran Thistlethwaite. And Hugh Morton and Elisabetta Beltrami show that if L is a link, then the arc index is bounded from below by the A spread of the Kauffman polynomial of L plus 2. Okay, so in the case of alternating link, alpha L is bigger than or equal to the crossing number plus 2. And Ben Park says alpha of L is less than or equal to crossing number plus 2. So in the case of alternating link, the prime alternating link, non-split alternating link, alpha of L is exactly equal to the crossing number plus 2. So yeah, so here's this. So this is a corollary. So if L is a non-split alternating link, then alpha L is equal to CL plus 2. So alpha L plus 2 is less than or equal to alpha, bigger than or equal to alpha of L by Baer and Bach. And this is bigger than or equal to spread of FL plus 2 by Thistlethwaite and Morton and Beltrami. And this is bigger than or equal to CL plus 2 by Thistlethwaite because L is alternating. Okay, so we know the arc index of alternating knots and links. So that's very easy. So if you know the crossing number, then we know the arc index. And for the case of non-alternating links, we have so myself and Park, different Park. So Wankun Park, he's in Seoul, and so one of my former students. So if L is a prime link, non-alternating prime link, then alpha val is not bigger than the crossing number, and the converse is also true. So there is no if you have a prime link, then the arc index is either C plus 2 or less than or equal to C. Okay, in the proof of, okay, so here's the so one sentence proof of this. So in the theorem, in the proof of theorem 1, I said there is a sequence of isotopic moves of moving crossing toward one special crossings, and so we proved that in this sequence there's a sequence of vertex reduction moves in which at two places we can do this move. Okay, so because it's non-alternating, so there exists a part that the two nearby crossings are along an arc is an overcrossing or undercrossing, and when you move this crossing over here, and you move this over here simultaneously, so that this triangle disappears. So this move reduces the number of regions by 1. So reducing the number of leaves at the end. Okay, and then you can do this at least twice. Okay, in a non-alternating non-split non-alternating prime diagram has at least 4 non-alternating arcs, non-alternating edges. So you can utilize 2 of them, basically. Okay, you cannot utilize all of them, so you can.
Is it what we can know easily? So you said.
Oh, okay, yeah. Okay, so if there is a non-alternating arc, so then you go along the arcs in this region. Okay, so there are more crossings. So along a region bounded by edges among which you have a non-alternating edge, then there has to be even number of non-alternating edges in one region. Okay. You cannot have an odd number of non-alternating edges along the boundary of a region. Okay, so there is another one, and then in this region you have another one, right? But if it happens that this region is the same as this, then this is a non-prime diagram. So if you have a prime diagram which is non-alternating, then you must have at least 4 non-alternating edges. So altogether even number. You must have you have only. You cannot have odd number of non-alternating edges in a link diagram. Okay, so that's the outline of the proof of this inequality. And here's a special case of non-alternating diagram, non-alternating link. A non-split 2-entangled T is called strongly alternating. So this is a two-entangle. So this is 6-tangle. We call it strongly alternating if these two ways of closing result in reduced alternating diagrams. So you just close the pairwise adjacent ones in this way, and the other way. So it's same as going the other way around. Okay. So if these two are reduced alternating, that means it's a minimal crossing alternating diagrams. Then we call this tangle a strongly alternating tangle. And if we have two such strongly alternating tangles, then we can produce a we can put them together so that it's non-alternating. Okay, and then we call this n semi-alternating link. This is a terminology of Beltrami, and she proved that if L is L is n semi-alternating, then the arc index is crossing number plus 4 minus 2n. So in the case of one semi-alternating, then it's a connected sum of two diagrams. In that case, it's crossing number plus 2. So doesn't go down, but if there are more arcs, then it goes down. Okay, and this diagram, this n semi-alternating diagram, is belongs to the category of adequate diagrams. Adequate, so it's of minimal crossings. And so the deficiency CL plus 2 minus alpha over L. So CL plus 2 is the number of regions in a minimal diagram, and alpha is the arc index. So this difference I call it deficiency. And then non-split alternating links have deficiency 0. So this is the proof. The Bear and Park result. And prime non-alternating links have deficiency at least 2. This is J and Park. And if L is n semi-alternating, then the deficiency is 2n minus 2. And in this case, the deficiency is equal to the number of non-alternating edges in the semi-alternating diagrams minus 2. Okay, the non-alternating edges in the n semi-alternating diagrams is equal to 2n. So it's just 2 less than the number of non-alternating edges. And this seems a case when the deficiency is maximal relative to the number of non-alternating edges. And notice that the 2n non-alternating edges are pairwise non-adjacent. They are spread, they are all apart. Okay. So in a diagram, the arcs between two adjacent crossings is called alternating if like this, and non-alternating if they are both on overcrossing or both undercrossing. Okay. So to get links with high deficiency, so we need to think about two things. So links which have relatively large number of non-alternating edges in minimal crossings diagrams may have high deficiency. So if we have more chance to do this, then we have the deficiency goes up. Okay, and as you see from in this case, all the edges are apart. Okay, so let me go back here. So suppose in this case this before this this end becomes is moved, the end, the crossing of the other end in the original diagram is moved into this, and before that, suppose that is non-alternating, then this non-alternating edge is not used to reduce the number of regions by 1. Okay, so if two edges are two non-alternating edges are adjacent, then you cannot use both to reduce the number of regions. Okay, so you reduce only by only one of them. Okay, so and in this case, these among all of these, except 2 of them, you can use all. You can use 4 of them to reduce number of regions, basically. So so links whose alternating edges in minimal crossing diagrams are well distributed. I mean, they are not as non-adjacent as they can be. Then that may have high deficiency. Okay, and so in the article I wrote with Lee, so she will give. She is the next speaker, and so that appeared in the most recent issue. Contains 372 knots of 13 crossings and 15 knots of 14 crossings, which satisfy alpha L is equal to CK minus 1. So this is a case of deficiency 3. The next 2 examples is one that satisfies this, and the other one does not satisfy this. Okay, so this is an example of alpha k equals ck minus 1, the deficiency 3 case. So here the red, so this is red, this is red, and this is red, and this is red. They are non-alternating edges. So there are 4 non-alternating edges. But if you do, so this is a triangular non-alternating triangular region. So you can do Reidemeier move 3, passing this arc over this crossing to get this. Then these 2 non-alternating arcs are still there, and here you have increased the non-alternating edges by 2. So 1, 2, 3, and 4. So from these 4 non-alternating edges, you can do 2 reduction of regions, and among these 2, from these 2, you can have 1 reduction of the regions. So altogether you can reduce the number of regions by 3. So in this case, okay, this is 819, and so its arc index is equal to 7. And this is so this is 2 left-hand twist, and this is 3 right-hand twist, and this 3 right-hand twist. So this knot is of type a pretzel knot of type -233. But the next one, which is pretzel knot of -323. So the 3 left-hand twist and 2 right-hand twist and 3 right-hand twist. So it also has 4 non-alternating edges, but if you do Reidemeier move 3, then here you have these are still there, and then so these 2 non-alternating edges become 4 non-alternating edges, but they are connected all together. So right, and in this case you cannot reduce the number of regions by 3. You can only do 2 reductions. So its arc index is the same as the crossing number. Okay. And so we go into the main topic, the pretzel links. So pretzel links of type P1, P2 through Pn is a link which has diagram like of this form. So you have two disks, and the disks are connected by twisted bands, and so if P1 is positive, then you have right-handed twist with P1 crossings, and if P2 is negative, then it has negative left-handed twist with absolute value of P2 crossings, and so on. But to utilize to do right move 3, we focus on 3 pretzel. Okay, so this region is so if one of them is minus and the other two are plus, then this is a triangular region, non-alternating triangular region, so that we can do right move 3, and you can do the same thing over here. And we only work in this case. P is bigger than or equal to 2. Q is bigger than or equal to 2 and less than or equal to R. And only one of, no more than one of PQR is even. If more than one of PQR is even, then you get a link. So I mean, the arguments may work for links too, but because but I just focused on knots. Okay. So these are the main results. So all right. So okay. So if Q and in the case Q and R are distinct, you can easily exchange Q and R without changing the knot type. So you can draw the diagram like this. So, but when you flip it, you have, if this diagram is minus PQR, and then if you flip it, it's minus PRQ. Okay, so so that's why we can have Q less than or equal to R. Okay. So here, in all of these triple minus PQR, only one of them, at most one of them is even number, and R is always bigger than or equal to Q. Okay. So here minus P minus 2QR with Q bigger than or equal to 3 and R bigger than or equal to Q. So because already we have an even number, I avoid that Q is an even number. So in this case, so the deficiency is at least 3. So alpha K is less than or equal to CK minus 1. So this is yeah. So this is one of the example. And in the case P is bigger than or equal to 3, and Q is equal to 2, and R is bigger than or equal to 3, then the deficiency is 2, only 2. So alpha K is equal to CK. For this case, if p is bigger than or equal to 3 and r is bigger than or equal to 3, the pretzel net of type minus p3r has deficiency 3. C alpha k is equal to ck minus 1. And if you have, in the case p is bigger than or equal to 5, q is equal to 4, r is bigger than or equal to 5, then the deficiency is 4. So alpha k is equal to ck minus 2. In the case of p equals 3 and q equals 4, r bigger than or equal to 5, then the arc index is either a c minus 3 or a c minus 2. So deficiency is 4 or 5. So the upper bounds of the arc index, we construct a diagram with this axis. So this is a case of minus 2 QR. So here you have two negative crossings, and you have Q right-handed crossings and R right-handed crossings. Then you can divide this diagram in this way by this red arc. Then this is the same diagram. Here you have one intersection, and here you have q minus 1, and here you have also here you have only two, this one and this one, and here you have r minus 1. So total q plus r plus 1, and the number of crossings in this diagram is q plus r plus 2. So it's one less than number of crossings. Okay. So this counting gives the proof of theorem 7, this first one. We were not able to find the lower bound for this case. And in the case of minus P2R, we have similar constructions. And in this case, we have, so here we have P minus 1 intersections by axis. Here we have 4 intersections by axis, and here we have R minus 1 intersections by axis. And P plus R plus 2 is equal to the crossing number. So that gives upper bound of theorem 8, and also theorem 8. Okay. And the next one, yeah, it's all similar. It's all even there is one more crossing here. The same counting works. So it goes down by 1. Okay. So the previous one was q equals 2, and this one is q equals 3, but we have the same number p plus r plus 2, so that's crossing number minus 1. Okay. And here's the counting. And for the case, so this case is more complicated than the previous ones. So this is so here in this case, P is bigger than or equal to 3, and Q is bigger than 4, R bigger than or equal to Q. So here there is so only this part is P minus 2 left-handed crossing. So here is another one, here is another one. And here you have a Q twist, and here you have R minus 2 twists. And this red curve here you have this piece. So we can reduce one of these crossings. So okay, so to do that, we do isotopy on this part. We fold it over here, making more crossings, 1, 2, 3 crossings, and then this intersection disappears. Okay, so and that gives on the leftmost case so one crossing, the next one is p minus 3, and the next one is 2, and the next is 3, and the next q minus 3, 1, and r minus 3. That gives you p plus q plus r minus 2. The deficiency is 4. So the theorem 10 and 11, the upper bound is ck minus 2. And for the lower bounds, we compute the A spread of the lambda polynomial. So for any link D, the lambda polynomial is of this form: sigma Fiz times a to the power I. And Fiz is some integer coefficient polynomial in Z. So here m and n are integers with m less than or equal to n. Okay, and Fiz's are non-zero polynomials in Z with integer coefficients. Non-zero. Okay, I mean Fm is non-zero and Fn is non-zero. So that wait a minute. Yeah. So Fm and Fn are non-zero, and the middle ones may be 0. Okay, and we use this notation: Fm z is equal to Km z to the power Hm, and Fn z is equal to Kn z to the power Hn, where Km to the power z to the Hm. So these are just highest degree terms in Fm and Fn. Okay, so we only focus on highest terms and lowest terms in this power I. And so in this case, the sigma Fiz ai is this times a to the n, and so this times a to the n, comma, this times a to the m. So this is the and we omitted the intermediate terms. Okay, so we only write I is equal to m case and I is equal to n case. Oops. Sorry. So m. Oh, so m is small. Okay, this is highest term. This is lowest term. Okay, sorry. Okay. So for example, this here is in the decreasing order of a power, and the highest a power is minus 1, the lowest a power is minus 3, and here the highest z term is z cubed, and here the highest z term is minus z2. Okay, and then in the case of two pretzel, so we can easily compute the lambda of 0, 0 is of this form, and so on. So we need these simple cases, and then we combine them to compute these simple. So this is a pretzel with no crossing in the middle, and this is pretzel with one crossing in the middle. And their lambda polynomials are computed using the previous lemma, and we have these simple cases. And then we combine them together to get these propositions. So in this case, the spread is crossing minus 2. So if you add 2, spread plus 2 is C is equal to C. Okay. In this case, spread is equal to crossing minus 3. So spread plus 2 is crossing minus 1, and so on. Okay, so that's all. Thank you.